So let's finish up the exercises in 1426, where we're using Grignard reagents to do some syntheses. And so here, if you notice on this molecule, on the left, the reagent, we have 6 carbons. And on the right, you have 1, 2, 3, 4, 5, 6, 7, and 8. Now, because you have more carbons here, you need to form new carbon-to-carbon bonds, and you would do that with Grignard reagents. So having more carbons in your products than in your reactants is a flashing light telling you to use Grignard reagents. And so to make a Grignard reagent, you take your alkyl halide and you dump some solid magnesium in there, and you form your Grignard. And so magnesium is a metal, it has very low electronegativity, and so this is effectively this nucleophile, with the magnesium and the bromine being like a counter ion with a positive charge. That sort of balances that out, but once it starts reacting, the magnesium and the bromine sort of go their own way in the beaker. So that's our carbon nucleophile. So we can go back to the molecule that we want to make. Here's our nucleophile. So the thing we want to attach is going to have 2 carbons. And if you notice, the functional group is on the first carbon. It's on the same carbon that the Grignard is attached to. And we talked about last time how if the functional group is on the second carbon, you would use an epoxide, but if it's on the first carbon, like it is here, you would use an aldehyde. An aldehyde being a molecule that has a carbon double bonded to an oxygen, single bonded to a hydrogen. And this carbon is an awesome electrophile, this carbon right here. First, because it's double bonded to oxygen, so the oxygen is really stealing a lot of electron density, so it's really pretty positive, partially positive. And also this second bond here, the purple bond, the pi bond, is weaker than a sigma bond, so it can easily break and the electrons can go onto the oxygen. So that's going to be a great electrophile for the nucleophile to attack. And so what we'll do is a similar procedure for last time. We'll draw those 2 carbons there, 1 and 2, like above. But instead of an epoxide like we were doing in the last video, we want to make an aldehyde on that carbon that the oxygen is on. So oxygen's on carbon number 1. That's where we want to have the aldehyde. So you make a double bond to oxygen, single bond to hydrogen. The oxygen is really electronegative. It's going to be slightly negative. The carbon it's bonded to, therefore, will be slightly positive. And so this nucleophile attacks that awesome carbon there. That carbon is called a carbonyl carbon. Carbon double bonded to oxygen is called a carbonyl. And so this carbon right here is the carbonyl carbon. So the Grignard reagent attacks the carbonyl carbon. The weakest bond, the pi bond, breaks. Those electrons go to the most electronegative place nearby. That's the oxygen there. And so now, here's our ring. These are our 2 carbons. The bond between the carbon and the oxygen is just a single bond because the pi bond broke. That gives oxygen a -1 formal charge. And so this is what we've got, which is really close to what we want, right? We want this here. The only thing we're missing is that hydrogen on the oxygen. And so to make that happen, as we've seen many times before, you just add some water, a good source of hydrogen. So water is really polar. The hydrogens are easy to reach. So this steals one of those hydrogens. The electrons go onto that electronegative oxygen. And you've got your product. So this is the reasoning. Let's just summarize the recipes we used. First thing we did was we made our Grignard reagent by dumping solid magnesium into our alkyl halide. Once we had that, we looked at the carbon chain that we were adding. I should say, we knew to make a Grignard reagent because the product had more carbons than the reactant. So we looked at the carbons we'd be adding. Easiest way to organize that, I think, is by numbering them. And we just repeated that molecule, just where you had the alcohol, we put an aldehyde double bond to oxygen, single bond to hydrogen. So we reacted it with that aldehyde, so that's step 2. And then last but not least, we just added some water so that the oxygen that was left here doesn't keep its negative charge. And so these would be the solution for B there. All right, how about D? Similar thing. If we look at the reaction on the left, we have, or look at the reagent on the left, we have 6 carbons. If you look at the reagent on the right, you would see that we have 6, 7, 8, 9, 10 carbons, so we have way more. That's flashing lights, a sign that we need to use a Grignard reagent. So let's turn this reagent on the left into a Grignard reagent. We do that by adding solid magnesium. And so that turns that alkyl halide there into this. And since magnesium, a metal, has such low electronegativity, it gives its electrons away to the carbon, which basically becomes this nucleophile. Okay, so now we have our Grignard reagent. Let's take that back. This is the carbon that would be doing the attacking. So what we want to add is this here. And so we can take those two. Notice that the functional group here, this oxygen, is on carbon number 1. And as we saw, if the functional group is on carbon number 1, the same carbon that the Grignard attacks, then it is, we want to use an aldehyde to make that. So we want to use an aldehyde to make that. So we're going to make this from an aldehyde, where we have that oxygen. Just put that there. Here's our aldehyde. And if this is carbon number 1 and this is 2, notice 2 has those 2 other methyl groups coming off, so we can just do that. So the oxygen is really electronegative, pulls the electrons to itself. The carbon it's bonded to is slightly positive because it's losing those. The nucleophile attacks that carbonyl carbon. The pi bond breaks, goes onto the oxygen. And so you are left with, so if that is carbon number 1 and 2, you'd have the 2 methyl groups coming off of there. The oxygen with just 1 bond, full negative charge. And so that's really close to what we want. We just need to get first a hydrogen on that oxygen. And we can do that by adding water. Oxygen slightly negative, hydrogens are slightly positive. The negative oxygen here steals an electron, or steals a hydrogen from the water. The electrons go into the oxygen. Okay, so now we have this. With 1 bond to the oxygen. We want 2 bonds to the oxygen, and so when you form more bonds to oxygen, that's an oxidation. And the way we learn to do oxidations is to add sodium dichromate. So this right here, create more bonds to oxygen, add Na2Cr2O7, sulfuric acid, and water. So we'll use that recipe here to take this bond here, 1 bond to oxygen to 2. So sodium dichromate, Na2Cr2O7, H2SO4, and H2O. I'll make another video that walks through the mechanism for that, which you would not be responsible for knowing, but you do want to know that that recipe causes this transformation. Okay, and so to summarize all the steps we took, the first thing we did was we made a Grignard reagent by dumping some magnesium in with our alkyl halide. We knew to do that because our product had more carbons than our reactant. Once we had that nucleophile, we needed to figure out what electrophile to react it with. Because the functional group was coming off of carbon 1, we used an aldehyde. So we made the aldehyde, we made sure the same branches were coming off of it, and so the aldehyde we came up with was this. And after that, we had this oxygen with a negative charge. To neutralize that, we added some water. And last but not least, after we had the water, we needed to make this alcohol a carbonyl. And we made that oxidation happen by adding Na2Cr2O7, so sodium dichromate, sulfuric acid, H2SO4, and water. And so these reagents are the reagents that would make this transformation happen. All right, F. So, in this left molecule, we have 1, 2, 3, 4, 5, 6 carbons. On the right molecule, we have 4, 5, 6, 7, 8 carbons. Different number of carbons, flashing lights. That's a sign we should probably use a Grignard reagent to make this new carbon-to-carbon bond. So to make a Grignard reagent, you take your alkyl halide and you dump some solid magnesium in there. So that gives you this molecule. And because magnesium, which is a metal, has such low electronegativity, this is effective. It gives its electrons away, and this is effectively this carbon nucleophile. That's how that's going to behave. Okay, so now that we've got our Grignard reagent, we know which carbon is the nucleophile, this one right here, we can think about what we need to add. So these are the carbons we need to add. Notice the functional group here is on carbon number 1. And that, we said, when that's on, functional group is coming off of carbon number 1, we use an aldehyde to make that transformation happen. So we want to make an aldehyde. Now I'm going to add those same 2 carbons, so here's carbon number 1 and carbon number 2, except on carbon number 1, where we have the functional group, instead of that functional group, whatever it is, I'm going to put an aldehyde. There are no branches coming off of carbon 1 or 2 besides that. So, the oxygen, very electronegative, pulls the electrons to itself, and the carbon it's bonded to in this carbonyl, which, remember, is carbon double bonded to oxygen, that's a carbonyl, and this is the carbonyl carbon. That carbonyl carbon is slightly positive. The Grignard reagent attacks it, the pi bond breaks, electrons go onto the oxygen, and so you have, at this point, this molecule. So here we've got carbon number 1 and 2, and this has a full negative charge. Okay, well, this definitely bears some resemblance to this molecule. It's a little far, though. First thing we have to do is to stabilize that oxygen. As usual, we can do that by adding some water. The oxygen is slightly negative, the carbons which lose their electrons are slightly positive, and so this negatively charged oxygen steals a hydrogen from water. Okay, and so we have an alcohol, and what we want to do is we want to turn an alcohol into, we want to replace an OH with a Cl. So we want to replace this OH with this Cl. And we learned how to do that using thionyl chloride. That would have been a thorough organic chemistry 1 class, would have gone over this reaction here. You can replace an OH with a Cl using thionyl chloride, and also a base called pyridine, so that's summarized by a PY. So again, I'll make another video that walks through the mechanism for that, which you would have gone over in Organic 1 class. You don't have to know the mechanism. What you should know, though, is that you can use thionyl chloride, SaCl2, and pyridine to replace an OH with a Cl. All right, and so to summarize what we did, we saw that the product had more carbons than the reactants, so we used the only carbon nucleophile that we know right now, which is a Grignard reagent. To make a Grignard reagent, we added solid magnesium to our alkyl halide. Once we had that, we saw where it was going to attach, and we deduced what type of molecule we needed to react it with. Because the functional group was coming off of carbon 1, we knew we had to use an aldehyde. And so we drew the corresponding aldehyde, which looked like this. Once we had that aldehyde, we reacted with the Grignard reagent. The oxygen that resulted from that had a negative charge, and so we stabilized that with a water. And last but not least, we replaced the alcohol that we formed with a Cl using thionyl chloride and pyridine. So SoCl2 and pyridine, which they summarize just with a Py. And so these successively would make this transformation happen. Okay, last one, I. This one is sort of a black sheep in this problem, but it would remind you, hopefully, of the previous problem, the one where you're trying to install two adjacent functional groups. We have an OH here, that's definitely one functional group, and you wouldn't normally think of this carbon chain as a functional group, but notice that you have these two adjacent carbons, and you sort of have two things that were added onto them. And so you can make this from an epoxide. So those two carbons, where you had the two branches sort of that you wanted to add, you can imagine having just an epoxide there. The oxygen in that epoxide is going to turn in to that OH. And so this other thing, when you draw this, when you draw the epoxide, just don't include the functional groups that you want to add. So this oxygen here is going to turn into the OH, and we need the other thing, this green thing, to be our nucleophile. Okay. And then one other connection is the double bond to the epoxide. So thinking about each of these carefully, one step at a time. First, double bond to an epoxide. We saw we can form that using a peroxy acid like MCP-BA, metachloroperoxybenzoic acid. So that turns the double bond into the epoxide. Once you have this epoxide, you want to open it up. The nucleophile you want to add is this green thing here. That's just carbon. Now it's 3 carbons. And you want this to be the nucleophile. And so, what you can really do is make this Grignard reagent. And that will act as that nucleophile. The nucleophile will attack this carbon. Electrons go up onto the oxygen. You would form those are those two there. Oxygen gets pushed onto there. And so if these were your 3 carbons, these are your 3 carbons right now. And to go there to your product, you just need to add a hydrogen onto that oxygen, which you can easily do by adding water. So this would go there, these electrons go there. So that was a little tricky. I would encourage you to compare this to the reactions from the previous problem, the ones where you're installing 2 functional groups on adjacent atoms. The one difference here is that the nucleophile you're adding, instead of being Cn- or SH- or hydrogen- from like lithium aluminum hydride, it's a Grignard reagent. Otherwise, this problem is really similar to the previous problems, where you turn first step, you turn a double bond into an epoxide by adding MCP-BA. You react the epoxide with a nucleophile to open up that ring. and then you add water just to neutralize the negative charge on the oxygen that pops open from the epoxide.